Hello everyone, my name is Jake Stringfellow, and this is my presentation for my computer vision final project for the spring 2023 class. For my project, I use a convolutional neural network to predict sign language letters in real time. American Sign Language is one of the predominant forms of communication used by deaf, disabled, or hard of hearing people in the United States and parts of Canada. For those who communicate through ASL, attempting to communicate with a person who doesn't know the language can be very difficult. Translation of sign language can allow greater communication between the hearing impaired and non-impaired, and thus it is a meaningful and important development. Sign languages rely on expression through motion and gestures, primarily by a person's hands. Sign language recognition is a fundamental task in visual sign language research and is considered to be a challenging classification problem. These visual challenges convey information using features like hand shape, movement, and pose. My program aims to solve this problem through deep learning techniques. The model is trained on a dataset representing the alphabet of American Sign Language. In the program, the user signs a letter in the region of interest, and the model predicts it. Among the papers I read researching this topic to prepare for this project, these 5 stood out to me. The study by Chen proposed a transfer learning baseline for sign language translation as a way to deal with the bottleneck that the lack of available sign language data places on the training of recognition models. Their proposal was the development of a system that has a model pre-trained on the general domain of human actions, another pre-trained on sign to gloss datasets, and then a module to link the two networks together to create a baseline model for future research. The study by Hu introduced a self-supervised pre-trainable model that specializes in recognizing hand pose for the purpose of sign language translation. Their approach to create effective models while working with less data was to pre-train the model by masking and reconstructing the existing data they had. The study by Chemgoes in 2020 introduced a novel transformer based on architecture that jointly learns continuous sign language recognition and translation while being trainable in an end-to-end manner. Their approach had significant performance increases across challenging datasets, and their research placed emphasis in recognizing features of input, along with the comprehension of signer interactions and movements in 3D space. The study by Chemgoes in 2017 proposed a novel deep learning approach to solve simultaneous alignment and recognition problems. By dividing the recognition problems into subunits as named in the article, they modeled the relationships between the subunits and solved the task. Their approach mimicked human learning techniques, and they learned that by better constraining the problem, they could improve performance. The last study by Collar took a novelty approach to weakly supervised video learning. Since this method was relevant to sequence learning problems and experimented with sign language, it was directly relevant to my project. It similarly exploited sequence constraint to the 2017 Chemo study. They embed powerful models following a hybrid approach to discover attributes that were not all distinct enough to be identified by models. They applied this approach to sign language by recognizing mouth shape, hand shape, and sign language in parallel. In order to be able to recognize sign language, the model would have to be trained on a dataset featuring plenty of signs, in this case letters, in a variety of backgrounds and poses. I chose the sign MNIST dataset because it was open source and was modeled after the classic MNIST dataset, which I was familiar with after the most recent assignment. It follows the same CSV format as the MNAST and represents the ASL alphabet. There's unfortunately no data for the letters J and Z due to those signs requiring motion to execute. I also realized later in the project's development that the sign for T in the dataset was not accurate, so we ignore it in the results. Each data case represents a 28 by 28 grayscale image with different users gesturing different signs in front of different backgrounds. They extended this set using data augmentation on the existing cases to create more data to work with. I implemented a sequential model in neural network class using TensorFlow's Keras framework. After plenty of experimenting with the architecture, I settled on the ordering shown in the top image. I used TensorFlow to compile the model, then trained it on the data I loaded from the two CSV files provided by the Sign MNIST dataset. I gave the model 5 epochs to train, and evaluating the data showed that the network was 92% accurate at predicting test data labels. Once the model was trained, I saved it for use in the main file. The main file begins by initializing the dimensions values for a region of interest rectangle, that is drawn to the screen to show the user where to create their signs. The user live video is opened, then a hand tracker is created to display the user's hand landmarks. These landmarks are based on MediaPipe's hand landmarks detection guide. We then load the model from the support file. During the live video, we save the portion of the frame in the region of interest to send our data to the neural network model. Before doing so, we first pre-process the image by converting it to grayscale, increasing contrast, decreasing brightness, then reshape it to be a 28 by 28 image with one color channel. The pre-processing is done to make the test frame as close to the training data as possible. That is represented in the ROI window on the left. We then have the model predict the sign in the frame and display the prediction made above the region of interest. For more accurate readings, the user should set up in a well-lit room with a light background. On the right side, you can see an example of the live video feed, where the region of interest is displayed as a blue rectangle, and the prediction by the model is displayed in small green lettering right above the region of interest. In the first one, it accurately represents the letter D, and in the second, C. The model performs well on its dataset. With this accuracy, I am confident that if given live data consistent with the dataset, it would be very accurate at predicting signs in real time. But unfortunately, live video presented some difficulties for the model with things like motion blur and inconsistencies between the test data and the live processed video. So as a reminder, the model does not predict T, J, or Z as explained earlier, but the model was able to recognize 20 of the remaining 23 letters when signed in real time. Some do work better than others, however, with 11 being recognized consistently almost every time. These letters are A, B, C, G, H, L, M, O, R, W, and Y. Some required some moving around and sometimes specific poses and positions to accurately translate. These 6 letters were D, F, Q, S, V, and X. 3 of the letters required extremely specific poses to work, which weren't always a good representation of the sign, and if deviated from, would result in an inaccurate prediction. These letters were I, K, and P. Only 3 of the letters couldn't be recognized under any circumstances from what I saw. These letters were E, N, and U. Each of these had a common factor. They share a very similar pose to an easily recognized sign from the dataset. E was mistaken for A, N was mistaken for M, and U was mistaken for R. On the top right image, you can see accurately predicting B. The middle image is a representation of V, one of the letters that requires some posing and some moving to accurately represent the letter. And on the bottom, you see the sign for U being predicted as R. This is because R and U are represented by very similar signs, and the model just did not accurately predict it. Considering the timeline for the project, the lack of a quality extensive data set used, I was pleasantly surprised by the results. Being able to accurately predict almost half of the letters was beyond my expectation when I first began the project. I do wish it was 100%, of course, but the fact that the model can predict 20 of the 23 signs, given certain conditions now, gives me confidence that with more experimenting and better data, I could achieve a much better and more accurate result. Going forward, I intend to continue developing the model and plan to incorporate the hand tracking system in a more prominent way. I would like to map the region of interest to follow the hand tracker's coordinates to allow the user to sign from anywhere in the frame. And eventually, I would like to use the hand tracking features to train another neural network. I will now play a demo of my program and end the video. Thank you all for watching.